By tracing its path back toward the disk of the Milky Way, astronomers estimate it was born over 10 billion years ago. Now that ancient ice is cutting a path right through our own solar system. Astronomers call this interstellar object 3I Atlas. Studying a visitor from outside our solar system is difficult. Earth-based telescopes constantly battle atmospheric interference, and because of our fixed orbit, we are often stuck with viewing angles that make it hard to track an object's exact characteristics. Because of these limitations, many interstellar visitors pass through our neighborhood as unresolved mysteries, leaving us with only a few blurry images before they speed back into the dark. But in November 2025, humanity had a highly advanced observer perfectly positioned out in the black, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE. JUICE was already flying through deep space on its way to the outer planets. When 3I Atlas appeared, Mission Control repurposed the probe mid-flight, pointing 5 of its primary science instruments away from its Jupiter trajectory and aiming them straight at the newly discovered comet. They wanted to know what happens when a spacecraft explicitly designed to scan the icy moons of Jupiter turns its lenses towards an object that has spent billions of years in interstellar space. While it originated in another part of the galaxy, JUICE's first major finding revealed that 3I Atlas is surprisingly familiar. It is essentially a standard dirty snowball. This visualization shows the scale of the activity. JUICE's spectrometer recorded the object spewing out 2,000 kilograms of water vapor every single second, enough to fill 70 Olympic swimming pools every day. This output falls comfortably within the range we see in comets from our own solar system. For comparison, Comet 67P, seen here, releases about 300 kilograms per second, while the famous Halley's Comet pumps out 20,000. Even though it was formed in deep space, its physical reaction to the heat of our sun is almost identical to the comets in our own backyard. As the probe peered into the haze of gas and dust surrounding the nucleus, its instruments noticed a specific behavior. The water wasn't coming directly from the solid core, but from icy dust grains evaporating on the sun-facing side. This diagram illustrates the chemical evidence of the comet's origin. Scientists look at the ratio between normal water, H2O, and semi-heavy water, or HDO, which contains an extra neutron. Using the ALMA radio telescope array and the Webb Space Telescope, astronomers discovered 3I Atlas contains an unexpectedly high ratio of heavy water. That chemical signature only forms in very specific environments. It indicates the comet was born in a freezing region and was exposed to high levels of ultraviolet radiation from young stars. While it acts like a local comet on the surface, its internal chemistry remains a perfect record of the deep space environment where it first formed billions of years ago. JUICE's ultraviolet spectrograph and high-resolution cameras also captured the physical scale of the comet's anatomy. The tail of glowing oxygen, hydrogen, and carbon atoms stretches outward into space for over 5 million kilometers. Because JUICE was flying deep in space, its navigation camera had a clear view of the comet during a window when it was completely invisible from Earth. This map shows Earth's blocked view, while JUICE had a perfect vantage point. ESA used this angle to calculate the comet's exact trajectory. By mapping this path, scientists now calculate the dust, gas, and debris left behind in our solar system. JUICE provided a crucial three-dimensional perspective, taking a fleeting streak of light and turning it into a precisely mapped physical object. When you look at all this data together, a clear picture emerges. The interstellar comet 3I Atlas is extreme in its origins, but it is not exotic in its behavior. It suggests that whether an icy body forms in our own solar system or 10 billion years ago in a distant part of the galaxy, the universe builds them using the same basic physics. This reinforces the idea that the laws of physics are consistent across the void. Our local cosmic backyard operates on the same rules as the rest of the Milky Way. Repurposing JUICE for this observation was a significant challenge. The mission required using instruments designed for stationary moons to track a fast-moving object from 60 million kilometers away. Despite these challenges, the probe successfully captured a comprehensive dataset that would have been impossible to collect from Earth. This success gives us a preview of what these instruments are capable of. If they can analyze a distant comet this effectively, we can only imagine what they will reveal when they arrive at Jupiter's icy moons in 2031. Long before reaching its target, JUICE has already demonstrated its versatility in deep space, turning a brief encounter into a detailed profile of a visitor from the ancient galaxy.